To begin with, I would like to express my sincere thanks and gratitude to Dr. Rao for inviting me to this meeting and to the organizing committee for their hospitality. So it's my intent to convince you that an antioxidant enzyme does more than antioxidant defense, and it has tumor suppressor characteristics. So this slide is nothing new. You all know the point I was trying to bring home is that cancer is an international epidemic. It's not a regional thing or a country thing. And so about 14 million new cancer cases. The data that we have available is for the year 2012 because it takes a lot of time to generate new data. And there are about 8 million cancer deaths. And right now there are about 33 million people are living with cancer, and about 12% of all deaths in the world are caused by cancer, and it's very cost prohibitive to treat cancer, especially in the United States. It has been estimated that to treat one breast cancer, it costs about $20,000, $100,000 US. This slide just brings the point that although the cancer incidence may be similar in Western countries and the less developed countries, but the cancer deaths are more in less developed countries compared to more developed countries. For example, you can see lung cancer, although there's more incidence in less developed countries, but compared to more developed countries, there's more death also. If you think in terms of breast cancer, it's almost same if you compare less developed versus more developed countries, but more people in the less developed countries die than the developed countries, and you know the reasons. It's the problem of not going to the clinics, early detection, and when you go to the doctor, it's present at mostly at stage 3 and stage 4, and doctors cannot do much. They are not gods. So prevention and early diagnosis is key to reduce cancer-related mortalities. So now, I guess I don't know why. Maybe, okay. So this is just an educational slide. We all know that how a normal cell kind of progresses from a normal to a neoplastic cell. So in the interest of time, I will not dwell too much on this slide. My laboratory is focused on understanding the biochemical and molecular mechanisms of hormonal carcinogenesis, in particular estrogen-induced breast cancer. And long-term estrogen use has been associated with the development of breast cancers. And these are some of the risk factors that I have listed here: prolonged exposure to estrogens, early menarche, late menopause, or even hormone replacement therapy, and obesity, because adipose cells store a lot of estrogen. And this slide shows that increased serum estradiol levels is associated with increased risk of developing breast cancer. And how do estrogens work? The predominant school of thought is that estrogens work through their cognate receptors. Estrogens will bind to estrogen receptors. Ligand receptor complex gets formed. There's activation, phosphorylation. It binds to the promoter regions and starts transcriptional activation of estrogen responsive genes. So, and the replication is not a foolproof process, and if there are errors and the errors are not repaired, then it may result in altered expression of cell regulatory genes, tumor suppressor genes, etc. But this classical mechanism does not show why some estrogens are carcinogenic and some are not. There are a number of synthetic estrogens which are estrogenically as potent as the natural female sex hormone 17-beta estradiol, but they either are poor tumor producers in animal models or not at all carcinogenic. So there must be some other mechanism rather than the receptor-mediated pathway that may play a role. So we and others think that oxidative stress plays an essential role in estrogen-induced carcinogenesis. So this slide is a very busy slide, but shows that the metabolic potential of some estrogens is a better predictor. The oxidative potential, the ability of estrogens to produce reactive oxygen species is a better predictor of their carcinogenic potential than their receptor binding affinities. So this shows how we think that estrogens can produce reactive oxygen species oxidative stress, and that can contribute to the carcinogenic process. 17-beta estradiol can be metabolically activated by cytochrome P451B1 to 4-hydroxyestradiol, which can further be converted as semiquinone and quinone. And during this process, it reacts with molecular oxygen to form a superoxide radical. Superoxide is the first of the reactive oxygen species produced, and that can be converted into hydrogen peroxide. Hydrogen peroxide by per se is not a reactive oxygen species, but can be converted if through glutathione peroxidase, it can be converted to water and oxygen. That's the major detoxification reaction. But if there's metallic iron or copper around, the hydrogen peroxide can be converted to hydroxyl radical. Hydroxyl radical is the most reactive oxygen species, which can damage DNA, cause point mutations, and can damage protein carbonylation, and also lipid hydroperoxidation. So if this damage is not fixed, then you can again feed into the same pathway, resulting altered expression of cell cycle regulatory genes. And tumor, to a layman, is nothing but uncontrolled cellular growth and proliferation. So this is how we think that estrogens play an essential role in inducing breast cancers. So in our laboratory and many other laboratories use this model, the female ACI-RAT model, to understand the biochemical and molecular mechanisms of hormonal carcinogenesis. This slide lists some of the salient features of this model, that no spontaneous mammary tumors are produced, and the tumors develop. First, you see ductal carcinoma in situ, and then adenocarcinomas, and the tumors develop after about 6 months after you give the estrogen, 3 milligram estrogen. Only 3 milligram estrogen is given as a subcutaneous implant, and the tumors develop about 6 to 7 months. And there's always a question, because you use exogenous source of estrogen, are using higher doses. But if you look at the normal circulating levels are 20 to 80 picogram per mil, but if you give these 3 milligram pellet, the circulating levels are 120. It's a little bit higher, but not supraphysiological. And this tumor model shares many of the histopathological and biochemical features with human breast cancers, as genomic instability, aneuploidy, and estrogen dependence. So this is, although it looks gross, but this is how the tumors, you can see palpable tumors after about 6 months. In the control vehicle treated, there are no tumors. You can clearly see the nipples, but you can see these bulging tumors after 5 or 6 months in this animal model. And so as I mentioned, that we treated them with 3 milligram pellet of 17-beta estradiol as a subcutaneous implant. And here this slide shows that with increasing estrogen exposure, there's increased morphological changes in the breast tissue, whereas in the control tissue, there's no significant change. They look normal. And the adipocytes, the fat cells, are progressively replaced by hyperproliferating lobular units, and they keep on pushing the fat cells, decrease the number of fat cells with increasing exposure to estrogen from 7 days to 7 months. And after about 7 months or 8 months, you see both ductal carcinoma in situ as well as invasive carcinomas. Invasive carcinoma, that's shown in this inset here. And I suggested that oxidative stress plays an essential role. So we measured whether oxidative stress is increased with increased exposure to estrogen. As you can see, that we sacrificed animals at 7 days, 15 days, 120, and 8 months, and dissected out the tumor tissue from the non-tumorigenic breast tissue. And with increased exposure to estrogen, you see increased oxidative stress as measured by 8-isoprostane formation, a marker of oxidative stress both in vitro as well as an accepted marker of oxidative stress, both in vitro as well as in vivo. So if oxidative stress plays an essential role, then if we do antioxidants inhibit estrogen-induced breast cancer. So we used two prototypic antioxidants, vitamin C and BHA. BHA stands for butylated hydroxyanisole, whereas 17-beta-estradiol produced 82% tumor incidence. The tumor incidence decreased about 24% when it was treated estrogen in combination with BHA, and to 29% when you co-treated the animals with estrogen and vitamin C. Not only did the tumor incidence decrease, but the tumor multiplicity also decreased, and the latency of tumor development increased from 128 days in case of estrogen to 183 days in case of vitamin C. So the purpose of this slide is to show that the morphological changes that you see in the breast tissue are not because of the antioxidants that we use, but because of the estrogen that we are using. And I showed a summary slide that antioxidants inhibit the development of breast tumors. Here I show that antioxidants not only inhibit breast carcinogenesis, but they also inhibit oxidative stress as measured by isoprostein formation. There's significant, at every stage, if you compare with age-matched control, there is a significant decrease in the production of reactive oxygen species. And so what we say that, okay, oxidative stress is involved. We wanted to see what's the molecular or biochemical mechanism and what genes are involved. So we did a microarray analysis, and this is just a histogram showing the microarray is a fishing expedition. Several thousand genes are upregulated and downregulated, and red means upregulated genes and green means downregulated genes. And so where do you start? So because our goal was to look at role of antioxidants, so we looked at the expression of antioxidant defense genes. So here, the number of antioxidant defense genes listed here, but I will concentrate today only on one, superoxide dismutase 3, which is about 18-fold decreased in the tumor tissue and about 3-fold decreased in the breast, non-tumorigenic breast tissue, which was exposed to estrogen. So these are the three superoxide dismutases that you are familiar with. You are familiar with superoxide dismutase 1, which is the copper zinc superoxide dismutase 2, which is manganese, the mitochondrial. Superoxide dismutase is an extracellular superoxide, which is least studied. And so I concentrate on superoxide dismutase 3, which our microarray studies showed that it's reduced in the cancer tissue, and interventions bring them back. So this slide shows that with exposure to estrogen, superoxide dismutase 3 is decreased both in estrogen-exposed breast tissue as well as in the tumor. But if you give interventions, it comes back both at the mRNA level as well as the protein level. In the tumor tissue, there's significant decrease, but when you give interventions, vitamin C or vitamin C plus E2 or BHA plus E2, not only does it come back, but it gets induced and increased. And there's a parallel between the increased expression of superoxide dismutase 3 and NRF2. NRF2 is the regulator of antioxidant defense genes. So we see that if you see a decrease in SOD3, you see a decrease in NRF2. And if you see an increase in SOD3 expression, you see an increase in NRF2. So suggesting that SOD3 may be regulated through NRF2, because if you silence NRF2 using siNRF2, you see a decrease in SOD3 itself, and also the same results are shown by chip assays. So, and if we use interventions, the antioxidants, we see that there's a decrease in 8-hydroxydeoxyguanosine formation, a marker of oxidative DNA damage. In tumor tissue, there's increased expression of 8-OHDG, whereas with interventions, it comes to basal levels. And if you silence superoxide dismutase 3, you see increased expression of 8-hydroxydeoxyguanosine formation, suggesting that SOD3 provides a protective effect. And the question is, okay, SOD3 is an extracellular protein. How does it protect from DNA damage? So we have shown that for the first time, that superoxide dismutase gets translocated to the nucleus. So here you can see we compare superoxide dismutase 1, 2 and 3. Among all these superoxide dismutases, only superoxide dismutase gets translocated to the nucleus, and this is the histology slide, which shows increased expression of SOD3, but SOD1 and 2, they don't translocate to the nucleus. And also, the point of presenting this slide is that SOD3 seems to protect the cells against carcinogenic insult. And if you silence SOD3, you see increased colony formation. You see, if you silence SOD3, you see increased mammosphere formation, and you see increased in GAP, the wound healing assay. That means that metastatic potential increases. On the contrary, if you overexpress SOD3, the colony formation decreases, mammosphere formation decreases if it's given SOD3 only alone or in combination with E2, and also the cell migration decreases. And SOD3 expression is also associated with decrease in expression of cell proliferation markers. If you overexpress SOD3, you see decreased expression cyclin D1 and PCNA, and I will come to this one a little bit later. So we also showed that the microRNA 93 regulates SOD3 expression via nerve 2, and that this microRNA can also do this, regulate the metastatic potential. And I will not, in the interest of time, not go into that thing. But this is what I wanted to show, that we injected nude mice with T47D is a breast tumor cell line. It produces tumors in nude mice. But if you use the same T47D cell lines in which SOD3 is stably transfected, there are no palpable tumors, and at necropsy we see a very small tumor, suggesting that SOD3 does have tumor suppressor characteristics. So to summarize, increased exposure to estrogens is associated with increased oxidative stress and increased DNA damage, that antioxidants can inhibit estrogen-induced breast cancer, and then decrease in latency, increase in latency and decrease in tumor size, etc., and that SOD3 is involved in the prevention of breast cancer, and that SOD3 is regulated by microRNA 93, which I did not show the results. Thank you. So I know at my stage of life, both at age and the career, I don't do much work. The work is done by these people, and I just sit here, come here to talk or to review the papers. Thank you very much.